256 possibilities, that is. And they apply fix-ups on page-in rather than being able to randomize binaries on disk. And this is due to a limitation that goes back to the code integrity and the ability to sign drivers and sign executables and stuff, and make sure that checksums match and stuff. So they can't manipulate the file on disk. They actually, on page-in, each page of the executable gets randomized. And again, the images are mapped to the same location. And although I kind of laugh at this, but if you take 1 over 256, you get 99.6% effective. Awesome. Well, we'll see. That I think there's some argument to that. But so, anyways, the heap randomization. So we covered the executable randomization. So now when they allocate the heap segment for the first thread, there's a random offset that's chosen using 64K alignment again. So that actually gives you 5 entropy, basically, from where the base of the heap would have been. So it's kind of shifted. And then stack randomization has a similar 5-bit entropy of the beginning of the segment, and then they cut that segment in half at the first page of that, and then it's actually D-word bounded. So it's every 4 bytes. It can be like any 4-byte alignment within the first half of that page. So again, these numbers are a little bit smaller than what you'll see in other implementations, but we'll see it's exponential when you say, well, I'm going to do a return to libc style attack, but then I need to be able to pass a buffer off of the stack. Those entropies get added up together because the complexity of 2 different random numbers is exponentially greater. So there's 3 pieces of the strategy. We've got the randomization. Non-executable pages are crucial as well. And then there's something that most other platforms don't use, which has been in Windows for quite a while, and it's the service restart policy. And so if you've ever gone to your services control manager, if you go to the properties of one of those services, there's a little tab that says, what do you do after the first time this program crashes? What do you do after the second time? What do you do after the third time? And so since this was already in there, they utilized this to kind of restrict the brute forcing of ASLR in Windows. So unlike PAX, which has great randomization, but you can brute force it 64,000 times, you actually only get 3 shots within a time window for Windows. And so with all these 3 together, it actually turns out to be a pretty effective strategy. The way those service restart policies work actually is there's a time window, and then within that time window is the 3 different states of what it can be. So all of the services on Windows Vista have been modified so that on the 3rd one they don't restart at all, so they crash and require an administrator to actually restart them. But logically, if you think about it, if you have a service and you're a server and your service is no longer providing the service that it's supposed to, well, an admin figure that out, right? So that makes sense. And then the non-executable pages are important because, if you can execute data, well, there's still going to be data mappings that aren't randomized yet, and we'll talk a little bit more about that. So our assumptions, again, were ASLR protects against remote exploitation. It's not going to protect you against local. And this is very simply because if I have the ability to run a local program and I can see where all the libraries are mapped in my program, well, I know where they're mapped in every other program. So we'll just say that ASLR is meant to prevent remote exploitation, things like worms and whatnot. It requires NX to remain effective. And again, that's because there are statically mapped data sections, things like shared user data and whatnot, that will be at the exact same location. And so those could be used maybe if you could figure out a way to get a little jump out of an address. Or actually another thing that Matt Miller researched a while ago was temporal return addresses, which if there's a timer in a data location that's not going to be randomized, well, on a certain day, in a certain year, in a certain time, you might be able to use that to go ahead and jump back to a library that'll get you code execution. And then again, so we've shown, or at least the guys at Stanford showed, that ASLR truly needs a limit on the number of brute force attempts. So the first strategy, of course, if those are the 3 things that ASLR requires to work, well, let's break them down and see what we can do about those. The first thing would be, how can we disable NX? Prior to Windows Vista, NX was actually really easy to disable. Most processes did not have a permanent flag, so that means the binary wasn't compiled with the permanent flag enabled, and so that meant that NX could be disabled in certain circumstances to retain application compatibility. So an example of this would be like if IE had NX turned on, which it doesn't, but if IE had NX turned on and you loaded a library into IE that said, I'm not NX compatible, then it would for the whole process, and so that it can continue to run. There's a few different types of DLLs that cause this to happen. If there's no relocation information for some reason, that would be if it's a DLL that actually just contains resources rather than code, then it doesn't need to be relocated. It just gets mapped, and then that references within that mapping. Or if it's loaded off of removable media, off a USB or a CD-ROM or whatever, then it would disable NX because it guarantee that that image is going to be there the whole time. And then also if there's another process or something that has an open handle to that file as data rather than like a code module, then it would also disable NX. So this was pre-Vista. And then of course there was an API called NT Set Information Process, which was published and to this day is still effective as a way to pretty much trivially bypass NX, and you can use that as kind of a return to libc call chain, so that if you're attacking a process that has NX enabled, then well, you can just go ahead and make your first return to a location. I believe it was NTDLL or something. It already has a call that's set up, so you just have one location you can return to. It disables NX for you, and then you can chain that back into wherever you need to. So that's still effective until Vista because of ASLR. So unfortunately, or fortunately, I guess for Microsoft, in Windows Vista, all those don't work anymore because NX cannot be disabled once it's been turned on in a process. And there's one caveat to this. There's a setting that you can set. It's kind of, they've replaced boot.ini, but it's kind of the equivalent. There's a setting that you can say, opt out of NX by default, so all processes are opt out until you enable each explicit one, and then those can actually be re-disabled. So that's not going to be a common configuration. It's kind of a test scenario, but in general practice, it will not be able to be disabled once it's been turned on for a process. Of course, this means not all processes actually have NX turned on by default, including IE. But anyway, so NX is kind of out as an option. The only real option is to target those processes that are not able to be, that do not have the NX flag turned on. So IE, Office, just a couple of little products that people use. But so anyways, the next strategy would be how can we make our brute force of ASLR more effective, since if we've only got 3 shots, well, you can't just sit there and keep increasing your address and hope that you're going to hit it. You pretty much have to be a little more strategic about how you're going to brute force. And so I came up with a couple of different ways. There's something called code symmetry, which would be if you look at the low 2 bytes of an address, if the same type of code or the same effective code execution will get you the same result. So in this case, we're trying to shift the stack pointer 20 bytes, right? So here's 4 examples of 4 different ways to shift the stack pointer 20 bytes. And you'll see the bold number in there at the end of each one of those addresses is important because this means that regardless of the executable that you jump into, at that offset, you're going to achieve the same effect. You're going to get the 20-byte stack shift that you're looking for. So in code symmetry, you're effectively making it so rather than having 1 out of 256 spots to jump, now you have 4 out of 256 spots to jump, or something along those lines. We did an analysis of this, and I mean, it's not a very high-risk thing. You might be able to put it to use in specialized scenarios, but if we identify anything that's kind of in there by default that could be used like this, it's pretty easily changeable, by the people compiling their software. But that's one strategy that you can put to use. Another one is the EI guys. They a tool called EEReap about 2 or 3 years ago now in Vegas, and it's actually pretty cool. It's an emulator that basically does, it goes through a crash dump of an address space at the time of exploitation, and it goes at each byte offset and starts disassembling. So in this case, since we have NX on it, would actually go at each executable page, and it would start from byte 1, byte 2, byte 3, and since x86 architecture allows single byte alignment for instruction, you can actually jump into the middle of an instruction and start executing from there. And so what this does is it really exhausts all possibilities of every single byte that you could jump into that would achieve perhaps a return to or jump to EBX, call EBX or whatever it is that you're looking for. It has a little logic built in. So I did some tests with this, and I found actually there's it certainly gives you a lot more possibilities of places to return. An example of this is I made a little hello world type example self-overflowing function type, very little code. And with a standard pattern match type of return address scavenger, I found something like 20 or 30 return addresses. Well, with EEREAP, it actually turned up like 140 or something like that, like a significantly large number of return addresses. And so, again, if you can get those return addresses and then you combine that with some code symmetry and stuff, the ASLR can certainly be broken down and made less effective. In addition, a commonly used strategy that's actually been used for a while to fight ASLR is using partial overwrites, because it doesn't require knowledge of the address space. If you already have a pointer at a known relative offset to perhaps where your buffer began, so you have a string buffer, and then somewhere down the road there's maybe, let's say 20 bytes later, there's a function pointer or something. Well, you know where that function pointer is into NTDLL. And you don't want to call the function that it's calling, but if you can identify a function that would be useful to you within a page forward or backwards or so, then you can just overwrite the low 2 bytes rather than overwriting the entire address. And so this requires zero knowledge of what that pointer's actual value is, because you just know that it's pointing within NTDLL, and if you shift it forward or backwards so many bytes, then you'll call a different function. So I think I have an example of a partial overwrite in a minute. And with within randomization in play, rather than sometimes you can take a controllable 4-byte write where you have control of the location that something's getting written, and then you have control of the data that's going to be written there. Well, with ASLR in play, you really can't use those for partial overwrites, because you're stuck with the original problem of where's the half of the pointer that I want to overwrite. So in the case of ASLR being in play, you can only utilize this when you have a bounded overflow. So you can control the number of bytes that it's overflowing. So you'll know that byte 35 is going to be overflowing the low 2 bytes of the function pointer, or whatever it might be. So an example of this, here's a little very, very simple program. Actually, it's not all the codes right there. There's 2 little stub functions. They're just little banner functions, banner 1, banner 2. And one of them says hello world, and one of them I think says you got owned or whatever. And so as you can see, there's 2 structures on the stack and a character buffer in between them. And this is going to overflow into that character buffer. And so when it overflows into that character buffer, it's going to overwrite the structure that's adjacent to it, and then eventually, if you let it keep going, it'll overwrite the return address and whatnot. Well, in this case, we can see that there's a function pointer being called off of that object that's adjacent to that character buffer. So if we were able to overwrite that function pointer, then we would gain code execution. And again, since we are in a randomized address space, what we want to do is only overwrite a couple bytes of that function pointer. And so we reduce the amount of our overflow just so that it just hits those last 2 bytes. So you can see the disassembly here. We get the address of the stir copy call. Go ahead and set a breakpoint there. Stop it right beforehand. We look at object 1. We can see object 1's function pointer points to banner 1 down there if you look kind of in the middle on the right. And then we step over and allow that string copy to happen. We've overwritten the lower couple of bytes, so it points to banner 2. And then when you hit go, it executes as owned instead. And kind of here's the example of the own is just a trigger word to do the overwrite. So that's just one example. In a randomized address space, that would work just as effectively as a non-randomized address space, simply because you're doing a partial overwrite. So that's another strategy you can use.